Okay, so now we really understand what we produced from that step one script, and we're ready to move forward and do new things. But it's a good point to just remind you that anytime we are facing a new script, we're opening a new script in the course, it's useful to just go up to Edit, Folding, Collapse All, just to sort of see this overview of what we're trying to get through. So we don't really need to talk about the introduction, and we already loaded packages in the last part of the lecture, and we examined our data, right? So we've already done these first three code chunks. The rest of the script, the new stuff, is we're going to generate some summary statistics. We're going to create our first plot using ggplot2. That's awesome. We're going to actually make a new kind of list called a digital gene expression list, or DGE list, using edgeR. And that's just a convenient way to store gene expression data, and you'll see why when we get there. And then as we discussed, you'll filter data, normalize it, and then I've sort of distilled everything from this step 2 script into this standard essentials code chunk. Okay? So we're really here on this fourth code chunk of generating summary statistics. Now, to do this, we're going to use base R's transform function, which operates on data matrix, and will modify it in some way, usually by calculating new columns based on existing columns. So I want to operate on my transcripts per million data, and I want to add 3 new columns, and I just name them here. They can be named whatever you want. In my case, I'm calling it SD for standard deviation, AVG for average, and MED for median. Now what I have to do is tell it what kind of data, what should populate those new columns. And what I do is I say, okay, that the data in that column should be equal to, and then I provide some function for how to calculate the data there. So the way to think about this, honestly, is this is really equivalent to Excel's equal, and I even say that here. You know, this is what would happen if you typed an equal sign in a cell in an Excel spreadsheet, and then typed in a formula. This is my formula. Calculate the row standard deviations for each row in my transcripts per million. Calculate the means for each row in my TPM, calculate the medians for each row in my TPM. All right, and I'll just say none of this is essential. You won't see it in the essentials code chunk. I'm doing it because I want to show you how easy it is to manipulate a data matrix, and also to highlight something that I referenced much earlier in the course. So when I execute this line of code, which again is really one line stacked here vertically, I create a new object called myTPMStats because I don't want to overwrite myTPM. And if I take a look at that myTPMStats, I can click on it and scroll over in the data browser. I can see standard deviation, average, and median. So I got these new columns, right, that I was after. I'm just going to close out some of these other things here. I could also look at that using the head function, which shows me the top 6 rows of any data frame or data matrix. And if I do that, I see that printed out to my console, which again, if I scroll to the end, I can see standard deviation, average, and median. Great. So the reason I did that is because I want to now introduce you to ggplot. And I want to make a simple plot that's actually a plot you've seen already. And this is an opportunity now to talk about ggplot. But to do that, I first just want to make the plot, right? And then we can talk about it. So the main function from the ggplot2 package is ggplot, and it needs some data. And the way ggplot operates is it creates a graph using layers. And the best way you can sort of structure this when you're writing the code is to actually stack the layers so that you can visually parse the code and understand what you're producing with each of these functions here. So I'm calling ggplot. I'm telling it it's going to be graphing this data. So the first sort of, component here is the data. And then I'm setting the aesthetics. What will the x-axis be? What will the y-axis be? What am I mapping my data to? What are the aesthetics? So I would like to plot the standard deviation on the x-axis and the median expression for each gene on the y-axis. Now, at this point, I haven't said anything about the kind of graph, right? And that's one of the sort of, I think, really useful ways that the grammar of graphics works is how do you describe a graph in coding language? How do you take a picture and actually accurately depict it and reproduce it using lines of code. So now that I've mapped the data to these aesthetics, I'm ready to choose whether I'd like the data presented as a points plot or a line graph or whatever. And so I'm going to use these geomes, geometric point, to create a point of shape 16 and size 2. All right, so I'm just going to actually run this single line of code. These plus signs help us stagger or stack the different functions we're running here. So I'm going to go ahead and run this line of code, and it'll produce a plot, again, of all my genes and all my data. And that'll pop up in the plots tab. This is the first time we've used the plots tab. And I see exactly what I asked for. Standard deviation assigned to the x-axis, median assigned to the y, all my data displayed as these point size 2, shape 16. And I see what we talked about much earlier in the course, which is this heteroscedasticity of our data, the fact that we have an unequal variance across a range of median values here. In other words, the most highly expressed genes tend to have the highest standard deviation. And we talked about why representing our data on a log2 scale helps with that, and other ways we sort of think about the impacts of count data and this heteroscedasticity. Okay, so you could play around with the point shape. I could change this to a 0.3 and rerun the whole code, and it doesn't matter where your cursor sits here, you just hit run. And I don't know what shape 3 is. It turns out it's plus signs, right? And you could keep going through this and change this to shape 7 and size 8 and run that again. Really easy to iterate over a plot and change the styles, the aesthetics, and virtually anything. All right, so as a quick sort of guide, the shape of the points on the plot are dictated by this menu. So initially, my point shape, I don't even remember what it was, something in this range, like a 20 maybe. But the number you choose for that argument dictates which of these you end up with. So you could plot your data. So with using 76, they'd all be L's, right? 25, they'd be red triangles. So if I go back over and I do shape 25 and size 3, and I run this, we're going to now see, red triangles as our shape. Okay. You can also easily change the kind of graph that you have. So, for example, I could change this to geome hex because I feel like I have a lot of data, right, buried down here. And this is something called overplotting, where I know there's a bunch of data points here that I can't even appreciate because they're all stacked on top of each other. So there's another kind of plot type, another geome type called hex that will bin my data and represent a bin as a hexagonal point on a plot, and then color that hexagon based on how many data points fell within its bin. So I can execute that new ggplot with that new geome, and now I see something very different. So here are my hexagonal bins, and I can see this one bin that's positioned here has most of the data in it. So, most of my genes are basically really lowly expressed, right? Very low median expression. That is totally normal, right? We don't expect all the genes to be expressed in all samples at the same time. So again, this really highlights that overplotting that we talked about before. Okay. Now, you'll notice the look of this graph is one that's always characterized by this sort of gray background with white vertical and horizontal grid lines. I could add a line of code to this ggplot by adding another plus sign and hitting return. And then I could add a theme. And you'll see it's giving me a couple themes to choose from, actually many. I'm going to choose theme just BW, black and white. I'm not going to set any arguments for this. In other words, I just want theme to be the defaults for the theme BW function. And so when I execute this line of code, now I get a plot that looks very different, a lot cleaner in my opinion. If you toggle back and forth between, what you can do, toggling back and forth between different plots in your plots tab, you can see the difference, right? I just got rid of that gray basically and replaced the white lines with gray lines. And this is a good time to just highlight that there's a lot of ways to sort of think about some of the looks of your plots. And so if we come back to our slide here, this idea of themes is one that just I want to make sure you understand before we move on, that the themes for ggplots are really complex, right? They have lots and lots of arguments. And so rather than you having to go in and tweak, which you could do, the theme, any theme function by sort of, dictating all the parameters for these different arguments, you can instead take advantage of the fact that ggplot has these complete themes that come with it. I used one of them, theme BW, but there's theme gray, light, dark, minimal, classic, void. And these basically come prepackaged with these different arguments set to different default parameters that give you a different look. And so these complete themes become a really useful way to just set a characteristic look for your graphs, all right, without having to dig in and actually, dictate these different arguments and set them to different values. So, the entirety of these arguments are contained within each of these functions, and you can just leave the parentheses open and closed and just choose the defaults. But you're not restricted to ggplot's complete themes, not by any means. In fact, many organizations that have sort of standards for how they display graphics have, bundled those standards into R packages. And an example is the BBC, right? The BBC has a certain color palette they choose from, a certain aesthetic, certain fonts they like for their graphs. And so you can actually use the bbplot package to give your plots, that BBC-like look, and you can check out their themes package, this bbplot package, to see what that theme actually encompasses. You can also use the GG themes package, which comes with a whole bunch of them. You can make your graphs look like they come from The Economist or the 538 or Wall Street Journal, or for some god-awful reason, I don't know why, old Excel plots, if that's your thing. But just to point out, there are many ways to sort of create a theme for your plot that gives fonts, colors, and aesthetics. I actually like this package called HRBR themes. We're not going to install it in this course because it can cause some issues for some of you, because it actually is pretty reliant on certain fonts that we actually don't often have on our laptop. So don't try installing HRBR themes, but it's another example of how, sort of opinionated some of these themes can be, and it really cracks me up. So here's a quote from the HRBR themes package documentation. There are nigh countless tomes written about the colors you should consider using in charts, as well as how to produce minimal charts. One area that's rarely discussed is the use of fonts, i.e. chart typography. The HRBR themes package is very opinionated about chart typography. So the HRBR themes package is really all about fonts and typesetting. I think really funny is that, typography nerds on either side of the serif versus sans serif debate, I didn't even know there was a serif versus sans serif debate, can point to 100+ years, really, of research-based evidence supporting their particular side. So clearly, and again, I love this package, the author is very passionate about fonts, and you can take advantage of that knowledge and passion and put that on your graphs. Okay, we'll come back to this slide in just a minute. So if we go back to RStudio, that same plot we just made, which was just an illustration of a concept we talked about in a much earlier lecture, that same plot can be elaborated on in a very easy way using this grammar of graphics. So here we had initially just 3 lines, the initial ggplot function, setting the aesthetics and setting the geom. But now we can expand on this, producing really the exact same plot, same data, but we can tweak many more elements. We can actually add additional layers. And this is a concept I really want you to understand about ggplot is that it constructs, it's got a layered approach to creating graphics. Each of these lines creates a new layer stacked on top of the previous. So to highlight that, I'm going to run this line of code, and I've intentionally done some things I wouldn't normally do. And we'll talk about that in the slides in just a minute. But I'm going to actually run this whole ggplot. It's going to produce the same graphic we saw, at least the same data, but now with some additional elements. All right. So as that displays, we can see now we have a curve fit to this. And I want to now walk through these exact lines of code, but in my slides, showing you that layered grammar of graphics and how that actually plays out. Okay. So this is that line of code. And now what I'm going to do is execute each line and produce the graph that would have been made had I stopped at that line. Okay, so really kind of hitting the pause button at each of these plus signs and asking what that plot would look like without the remainder of the code after it. All right, so we'll start here, and we know what that looks like because we already made it. But now let's do the next layer. Geom smooth will fit a curve to the line, and geom smooth is a way that we can set a particular method, in this case a linear model fit to the line, to the data. I could then, if I wanted, do an additional plot on top of that. So there's no restriction here to choose a plot type. You just have data and aesthetics and a variety of different geoms that you could access. So if I plot a geom hex on top of this, I can actually see where it overlaps, and you can see what some of the initial points from the geom point sort of peeking through here. But those are the data points that got binned into these hexes, right? Moving on, now I've applied a labels to the y and x axis, median and standard deviation. So we're going to see the med and SD be replaced by those labels now. I continue in my labels function here to add a title, transcripts per million, there. And I continue to add a subtitle, which will appear under transcripts per million, unfiltered, non-normalized data. I can even add captions, which can describe some additional information about the plot, and we'll use these for all of our plots moving forward in different ways. In this case, just saying the name of the course in spring 2020. And then now that I have the graph that I want, I can start to change the aesthetic, the theme. So the classic theme, the dark theme, and the theme BW. Each time, had no problem applying 3 different themes to the graph. It just stacks them on as different layers. So what advantage does this idea of a layered grammar of graphics offer us? Well, you can iteratively update a plot, changing specific elements as needed. Each line is a layer. Even high-level aspects of a plot can be changed, like changing from a point graph to a geom hex to other kinds of graph types. Layers allow your plots to be overlaid, not overplayed, probably overplayed too. So you could have a box plot with your points shown. Layers also make it easy for you to use the pound sign as a comment hashtag to toggle different layers on and off, right? It's very easy to go into that code and turn off 2 of the 3 theme layers that I used. Default arguments for each layer really minimize the need for you to dictate specific arguments or details. So you could simply, put in a layer and just have an open and close parenthesis. And then for the software developer, which is not as relevant for this class, it's easy to develop new functionality because you can think of it in terms of a layer. You could develop a new layer function, if you will, that lets you do something to a larger graphic. Okay. So now you understand this layered grammar of graphics approach and how you can really construct a really detailed plot from using the ggplot2 package. Okay, so that then moves us into a totally different part of the script, which is actually bundling our data into something called a DGE list. I mentioned this earlier. We'll use this DGE list function from EdgeR, and we'll give it our counts. And this is really important. We're not giving it transcripts per million. Even though we worked really hard to make these transcripts per million, the reality is Lima, EdgeR, DESeq2, they want to operate for statistical reasons. They want to work with raw counts. So we're going to give it the counts, and it's going to use those counts, and that's all it needs to create a DGE list object. So I'll run this line of code now. And there's my DGE list. It is a formal class DGE list, meaning it's this special data structure that the developers of EdgeR created, but it's really a list object. We can take a look at that by just either highlighting it or executing a line of code with just the name of the object itself. And what we can see is that it has two elements to it. The first is $counts. So we could access that by typing DGE list $counts. And it's a data matrix, right? It's our gene symbols as row names, and then our 10 samples. Sample labels were dropped, and this happens a lot in R, but remember we captured our sample labels and can always throw them back on. It never changes the order of them. And these are our raw counts. But it has a second element called samples. And this is really my individual samples or libraries, how many reads there were that mapped from that sample to the reference. That we call that the library size. And then the normalization factors, which currently we haven't normalized. So these are all sort of weighted equivalently. They're all listed as one. And we've assigned no groups or anything here, even though we know there are two groups. We're not going to really deal with that in this case. Okay, so we understand what this DGE list is. This is actually a third on-ramp into the data analysis that I haven't really talked about, is that you could give somebody a DGE list. It's a common data structure in Bioconductor that's really useful for RNA-seq data. So you could save my DGE list and just give it a file name, and it'll actually appear if I run this line of code and I go over to my file directory. It'll appear here somewhere. There, my DGE list, right? So this is how we use the save function to actually save an object from our R environment to our hard drive. Sort of the opposite of read TSV when we pulled data in. And then if you ever want to pick up on an analysis with a DGE list, whether it's your own or somebody else's, you just use the load functions, sort of the opposite of save. It pulls an object, an R object in from your hard drive into your R environment, and you just have to tell it the name of it, right? So I can load that back in. Okay, now that we've done that, we're going to take this DGE list object and we're going to extract the counts per million. So it's going to use those raw counts and it's going to come up with counts per million. This is sort of the equivalent of transcripts per million, but at the gene level. So I'm going to run this, and I now have this object called counts per million that if I run the call sums on it, they all tally up to 1 million. Okay. If I wanted to, I could have, and just to show you as an example, I could have run the exact same thing, counts per million of my DGE list, but I could have said log equals true. And the CPM function, which is actually from EdgeR as well, will then take the counts out of the DGE list and log2 convert them first. And that's the default is log2. So I don't have to say log2 versus log10. I just have to say true. Now when I do that, I end up with a different object, which is log2 counts per million. And we talked about why that's useful for dealing with issues like heteroscedasticity. Okay, so we know how to create a DGE list. We know what it looks like. It's actually really simple. And we know how to then extract counts per million or log2 counts per million from that DGE list in a really, really simple way. Okay, but no matter what we've created here, CPM or log2 CPM, they are all data matrices, right? They all have row names separate from the data itself, and then numeric data that makes up the entire spreadsheet. So that's a problem insofar as to work with the tidyverse set of tools that we just talked about. That only works on data frames. So we're going to do something called coerce or coercing our data matrix to force it to be a data frame. And one thing we have to do when we coerce this log2 counts per million to be a data frame is it's going to drop our row names. And this is just this fundamental disagreement between a matrix and a data frame. Is a matrix respects row names, and a data frame is like, I don't understand why you have this separate thing called row names. They should just be another column in your data. So we tell the asTibble function that when it converts this log2 counts per million data matrix to a data frame, to a tibble, that it should actually take the row names and store them as a column called gene ID. All right. Otherwise, it's going to actually drop them. And it's not hard to get them back. It's just a character vector of gene symbols, but we want to just go ahead and tell it, create a tibble from this matrix and store the row names of that matrix as a new column called gene ID. And it's going to put that entire thing in an object I've called exactly the same name I did up here, log2 counts per million, but .df for data frame. And that just helps me distinguish it from this data matrix. I'll execute that line of code, and I'll take a look at that object. Because it's a tibble, it prints out on the console nice and neat. Tells me it's 35,643 rows by 11 columns, and 11 columns instead of 10 because it went and put my row names as a column. So now I have gene ID, a character vector, right, a character, and this numeric data here, samples 1 through 10. And it does the thing that a tibble does. It highlights negative numbers in red, positive numbers are white. It underlines different sort of decimal places, etc. Okay. Now that we've coerced our data matrix to be a data frame, we'd like to add our sample labels back to this, right? Currently, they're just these ambiguous sample labels. And I told you that happens from time to time as we sort of wrangle our data, we'll lose sample labels. But that's really easy to put back because we can use the call names function and operate on this data and say, hey, I want the call names of my data to be this. Now, what is this? We haven't really talked about this. The first is a function that's just a concatenate function, and it's just really as simple as writing the letter C. And it will take anything you put in parentheses separated by commas and concatenate it together as a character vector. So actually, if I just highlight this portion of the code and hit run, you can see that it creates a character vector of the literal character gene ID, then with all of my sample labels in that sample labels object that I created at the top of this script. It strings these together. This was a character vector of length 10. This is a single character. And so it puts them together as a character vector of length 11. And that's perfect because I know I have 11 columns that start with gene ID and add my sample labels. So all I'm doing is overwriting the first column with the exact same name and then adding the sample labels to the remaining columns. When I do that, and then I look at my log2 CPM data frame again, now I have gene ID and my sample labels. Perfect. If I had left this off when I first ran this data, left off, the gene ID and just piped in my sample labels into the column names, it would say, okay, fine, I'll do that. And then when you look at the data, it would have replaced the first column, which is gene symbols, with the first sample label. And it would leave NA for this last one because it had nothing to throw on as a label there. So that's why I had a character vector of length 11 where the first was just overwriting the original. Does that make sense? I hope. So now we have our appropriate data frame here with gene ID and our samples. Okay, so now that we've added our sample labels to this data frame, we're in a really good place, right? We have a good data frame of our gene expression data with sample labels and gene symbols present, and it feels like we're kind of ready to make graphs with this data instead of these demonstrations of stuff we talked about earlier in the class, but we're not really ready yet. And the reason we're not is because this is messy data. So this is a good point now to talk about this tidy data philosophy. And so then hopefully if you understand this, you understand why we're going to do the next and last steps in the code. So a data set is messy or tidy depending on how the rows, columns, and tables, if there's more than one of them, are matched up with observations, variables, and types. We're going to kind of break that down. So basically, for data to be tidy, each variable needs to form a column, each observation needs to form a row, and each type of observational unit forms a table. This third point's not so relevant to us because we don't have multiple tables in our data, but these first two are directly relevant. Each variable needs to form a column, each observation needs to form a row. Messy data is anything that doesn't meet these three criteria. It's a bit like the Anna Karenina hypothesis. All happy families are alike, all tidy data is alike, but each unhappy family or untidy data is unhappy in its own way. And I think a lot of data scientists would tell you that they spend a tremendous amount of time just trying to get their data into form, into a shape that it's ready to be graphed and mined. And that's really what the tidier package in the tidyverse deals with, is how to get data that's unhappy into this happy state. So let's take a look at gene expression data, right? So I would argue gene expression data is always messy because we're always dealing with genes as rows, treatments, conditions, samples as columns. And so that would be the definition of messy data. Why? Because we have to remember every variable has to form a column, every observation has to form a row. To make this data tidy, we would need to take our variable, right? Every variable should form a column. Well, one of the variables is treatment, and it doesn't form a single column. It's spread across multiple columns, treatment 1, treatment 2, treatment 3. Each observation should form a row. So the tidy version of this data looks like this. Gene A, treatment 1, expression level X. Gene A, treatment 2, expression level Y. So that's tidy data. And to get from messy to tidy data, we're going to use this pivot longer function from the tidier package. And as I said earlier in the lecture, I feel like tidier as a R package is one of the more complex and sophisticated packages. So we're really not going to dive into all the multitude of things it can do to data sets. We're just going to use it for this purpose for now. All right, so you can convert sort of tidy data, what we also call long data, to wide data by using the pivot wider. That'll take you back here. So there's functions to kind of go between these two shapes of data, wide and long. So why is tidy data ideal? Why do we want it? Because it's great for graphing. So each variable gets its own column, so we know how we can find variables really easily and use those to make plots. And each observation gets a row, so those become data points on our plots. And really the values we want to graph now are easily retrieved as like a single, numeric vector. Okay, so let's come back to this in just a minute. Let's go back to the script. And now let's actually use this pivot longer, right? And now you know why we're using it, because right now our data is messy. It is wide and not tall. We have genes, or sorry, not genes. We have patients, which should be a single variable. Patient should be the variable, is actually spread across all 10 columns. So we're going to tell pivot longer to operate on this data frame, and that it should be looking at columns 1 through 13, right? Columns HSO1, this, through CL13. And when it looks at those, it should convert those columns as a variable into a column called samples, and convert all the data under those column headers into a single column called expression. So operate on this data on these columns, convert the names of the columns to samples as a new variable, and convert the values in the columns to a new column called expression. And put that entire operation into this new object I'm just going to call the same thing, and pivot. Remember, no spaces or anything in the names of our objects. When I run this and I take a look at what I've created, now I see I successfully transformed this wide and messy data set into a tall, tidy one, where genes observations are listed as rows. The samples is a single column now, and the expression data is a single column. Remember, this now makes this expression data really easy to retrieve. Okay, so now that I've pivoted this data in this way, I can tell ggplot, go get this pivoted data. Sample should be my X column, expression data should be my Y, and I want you to fill based on the, fill the color based on the sample. So each sample should be a different color. I tell it I want a violin for the geome, so that's the shape I want plotted, and that I want a statistical summary of my data. This is something we hadn't talked about yet that's available to you in ggplot, is you can do different statistical summaries where the function is median. I want a shape that dictates where the median is. That shape I know that I want is 95. I don't need to get into the details. And then I want some labels, and I want my theme at the end. So now I think, even though this is kind of a long ggplot, you understand what's happening. And when I execute this line of code, we're going to get our first plot of our data. All right, so as that comes up, remember, we're going to be plotting every sample on the x-axis and its log2 expression on the y. I can see every column, every sample got a different color. That's because I told it to set the fill color to correspond to the samples. And I was able to do that because the samples weren't spread out across different columns. They were a single column retrievable as a character vector that allowed me to bin expression data by sample. And in a similar fashion, the expression data was all retrievable as a single numeric vector, right, that could easily be binned by the sample it was assigned to. So I know nothing about individual genes here. I'm not asking about particular genes. I'm asking about the distribution of data, all the genes for each of these 10 samples. And I can see that there's this giant hump here at the base, right? A ton of stuff that's either lowly expressed or not expressed at all on a log2 scale. And then this sort of long tail and a bump here at a log2 of 5 that indicates there's some stuff that's highly expressed. I have no idea if that stuff is the same in the disease samples as it is in the healthy samples. I just see the distributions. It'd be unusual if these distributions look dramatically different between samples. This is something to kind of look out for. You can sometimes spot outliers at this point. But I can see that I have a lot of stuff down here that is not expressed. And anytime we're dealing with a large data set, we look for opportunities to trim down that data and sort of remove the fat. And this is definitely the fat. The stuff that's not expressed, it's not informative. We're not going to care if it's slightly different in this sample than this one. If it's not expressed in most of these samples, we want it taken out. Okay, so that's really where we are now. You could, and I give you different examples down here of sort of ways to think about what we're doing and new things to try, like, for example, flipping the coordinates on this plot, for example, here by adding a plus sign and adding the function coord flip and rerunning this graph. And now, and this is useful if you have long sample names that don't fit well on an x-axis, by running coord flip, now they fit nicely here. They're much more readable. You can see one issue with the layered grammar here is my symbol or stat median I used. I told it I wanted a horizontal bar and it gave me a horizontal bar, right? I would probably now want to change this to be a different shape, not shape 95, but a shape that's a vertical bar now that I've rotated my graph. Okay. Now that we've done that, we're going to move more quickly because we're really not doing anything different the rest of this script. We're going to filter our data and normalize it, but those are two simple operations in terms of the code. And then we're going to generate exactly these kinds of graphs again, because the idea is we want to be able to visualize what the impact of that data was. So in order to filter our data, we're going to take this DGE list object and we're going to ask how many of the samples had 0 counts in all 10 of the samples. So this is really a logical vector operation here. And I've broken it down in terms of what I'm doing from starting inside and working my way out, right? Asking for a logical matrix of all the genes for all the counts in my DGE list, how many were 0 across all 10 of the samples. And then I can use that information and summarize it using the table function. And I encourage you, I'm going to sort of gloss over these details because it's written right here exactly what I'm doing. But I'm going to run this line of code, and I can see that by using the table function, I can summarize the result of these sort of logical operations and see that, 29,610 of them were not 0 counts in all 10 samples, but 6,000 of my genes were. So, a substantial 10, 20%, 20% of my genes had no counts in all 10 of the samples. All right. I'm not doing any filtering at this point. I'm just looking. I'm just looking to see sort of what might constitute this giant bulge at the bottom. How many genes are we talking about? Now that I have a sense of things, now I'm actually going to filter. I don't need a special package to do this. I can use the row sums function, which is sort of base R function. And I'm just going to say how many genes had a counts per million greater than 1 in greater than or equal to 5 of the samples. And you can filter using row sums on anything you want. You could filter on your raw counts. You could filter on the counts per million. In this case, I'm saying how many genes, right? How many rows had counts per million greater than 1 in greater than or equal to 5 of the samples. Why 5? 5 because I have 10 samples in my data, but I know they sit in groups of 5. 5 samples from healthy individuals, 5 samples from patients with cutaneous leishmaniasis. I'm trying to avoid a situation where, for example, if I set this to 10, that there might be for example, a gene that is very low or almost absent in my 5 healthy subjects, but goes way up in my 5 patients with disease. And being strict like this and asking it to be over a count per million in all 10 samples, I might accidentally filter those out. So by setting this to 5, I tend to set this to the sort of smallest n of the n of my smallest group. So this is going to tell me how many, if I just highlight and run this, for each gene in my data, whether it satisfies, true or false, those criteria, whether it meets those criteria. So was it greater than 1 count per million in greater than or equal to 5 of the samples? And you can see that many of these were not, so they were not greater than 1 count per million in 5 of the samples. But the ones that are, I want to actually keep those, all right? And I call them keepers. Again, keepers here is just a logical matrix of falses and trues that is telling me whether a transcript like this one was indeed more than 1 count per million and greater than or equal to 5 of the samples. What I can do with that then is I can say, all right, now that I have this information, I'm going to use that to carry out a subsetting operation. And we haven't talked about subsetting yet. We're going to use this a lot. It's a base R functionality, and it's incredibly useful. The way subsetting works, we can take an object like my DGE list here in this case, but you could also do this with data matrix, and we will tell it which rows and columns we want to remove or keep. You get to do either. The language we use to talk about that sort of subsetting is really, really simple. It is brackets, open and closed, with a parenthesis, with a comma in the middle. Any rows or anything we want to do to rows, we put on the left of this parenthesis, and anything we want to do with columns, we put on the right. Now, you don't actually write columns and rows. I just wrote that so you understand what we're doing. But if I wanted to only take row 5, it would say 5, comma. Again, rows on the left of the comma, columns on the right. If I wanted row 5 of column 10, I would write it like this. And this kind of thing can continue where you can make a concatenation of rows 1, 2, and 5 for column 10, right? So it becomes really easy once you understand the subsetting operation to write it. And it doesn't just take numeric indicators of which columns or rows you want. It can also take logical vectors or for subsetting operations. So in fact, I can take keepers and subset the myDGEList object. So you always put the object that you want to subset first, followed by the brackets, and that comma in the middle will dictate whether you're taking rows, columns, or both. All right. So I'm going to take myDGEList and I'm going to use keepers to select rows, right? I want the rows, the genes that correspond to true. And remember, every time we use logical operators or logical vectors or carry out logical operations, we're by default using the true value as the thing we select. So when I run this and I look at the dimensions of the object I created, it's actually up here, but I'm just going to use the dim function to look at the dimensions. I can see I now have an object that's 15,944 rows by 10 columns. So I removed more than half of my data by just taking out any gene that didn't have more than 1 count per million in at least 5 of the samples. Is that the right way to filter? There is no right way here. You just need to think carefully about the size of your groups, how stringent you want to filter, and that should really drive what you do. Once I filtered the data, I'm going to do exactly what I did before. I'm going to take that filtered data and I'm going to turn it into CPMs, log2 converted. Again, this is just for graphing, right? I'm going to convert it into a tibble. I'm going to set the column names, and I'm going to use the pivot longer function. So I'm really just doing that data wrangling again that I did up above, but this time to make this graph, but with my filtered data. So we should see a big change to the data that's down here. Okay, so that should show up in just a second. Oh, right, so I just pivoted. I haven't plotted yet, sorry. Let me plot. And now we'll see the impact of that filtering. Big change, right? Now those distributions have shifted up because we cut off all the stuff down here, or almost all of it, right? Anything that was down here in 5, basically 5 of the 10 samples, or sorry, at least 5 of the 10 samples was taken out. Now we do one last operation to our data and we're done. We plot it again and that's it. And that last operation is we use the calc norm factors from EdgeR to normalize our data, and that uses this trimmed mean of M values that we talked about and that the papers on last week's reading assignment, this TMM method to normalize, to carry out between sample normalization. So we're going to carry that out on our filtered DGE list, the thing we created up here, right? The filtered DGE list. And so now we've taken our filter data, we're normalizing it, and we understand that we're applying this normalization method TMM. All right, if we highlight this normalized DGE list and we look at it, one thing to point out, we're still dealing with a DGE list object. It's got 2 elements, counts, dollar counts and dollar samples. But the thing you'll notice now is that the normalization factors are now not all 1, because it has looked at this between sample comparison and it's adjusted these factors to help us control for differences in these distributions. So we can see that some of these are tweaked down a bit, some are tweaked up, above 1 and below 1. Okay, now we're back to that same operation, right? Now that we've normalized the data, we extract the counts per million from the DGE list, we convert it into a tibble, we make sure we've got sample labels on the row names, we pivot the data, we plot, okay? And now we get our third plot that now gives us an idea of the normalized data. Doesn't look much different, but if you toggle back to the previous one, back and forth, basically like a flip book, you'll see this little bump, right? So normalization did help to kind of, bring those distributions together a bit, but it is subtle, all right? Okay, lastly, I have a bit of code down here I'll let you play with, which is, what if we saved these ggplots instead of printing them to our plots window? What if we save them to something like, we'll call this p plot 3 here, right? So we can save ggplot objects, plot3, plot2, oops, and back up here as plot1. Sorry, I'm getting tired, so I know you must be. All right, so I'm going to run these three ggplots again, and just it stores the result in that object P1. It's a large gg. I'm going to go down to run this one, and go down to my third plot and run that one. And what I can do now that I have these three ggplot objects, you can do this with as many and as varied graph types as you want. I can use the cowplot function or cowplot package that we discussed at the top of the script and use the plot grid function to stick together plot 1, plot 2, and plot 3, give them figure labels, and dictate the label size. All right, I'm going to make my plot window a little bit bigger here because I know this is going to be big. And I'm going to execute this line of code, and we should get all three plots all laid out in a grid for us. And because there's three, it's still thinking. Because there's three, it's not going to be an even grid. There's going to be two at the top and a third one. All right, once that prints out, we're really done. We've created our graphic, and it looks like I still had that coordinate flip on for the first one, so I can always go back up and take that off and rerun just that P1, plot 1, come back down and replot that so that they all look the same. All right, while that's displaying, the only difference you'll notice in these plots that we haven't really talked about yet, and this is coming up now, is that in my caption that appears at the bottom, I've actually told it to put together the word produced on, and that's the paste function. Paste will put together any number of things you dictate in the parentheses with zero space separating them. So I said produced on space, and then the system time from my computer, which is just a function I'm running with no arguments. It'll spit out the date and the time in a 24-hour clock and stick that on the bottom of the graph. So I'm time stamping the plots. Now you can see unfiltered, non-normalized, filtered, non-normalized, filtered, TMM normalized. All right, so just to close then, this is really what we did. We took the raw data, converted it to a tibble, pivoted to make it wider, pivoted to make it longer actually, and then ran ggplot. We then used the base R function row sums to filter that data, and then did the same thing, then used the edgeR calc norm factors to normalize, then did the same thing. So I know this was a long script, I know this was a tiring lecture, but you understand now how to use ggplot, how to use these functions, and how to kind of iterate through these different graphics as you're working with your data. Okay, that's it.